it's a weird question. Looks great though. It looks really hard.
Okay. So this is number 3. This had the lowest success, so let's do it. So for number 3, we've got y equals x to the 2/3. If you didn't know what that looked like, that'd be reasonable to use your graphing calculator for that, but it basically looks like this. But it's also defined for negative values of x. You can take the cube root of a negative value. So I think it looks something like this. And x equals 1. And y equals 0 is, what's y equals 0? The y-axis? X-axis. So a lot of students make that mistake. So what are we talking about? This right here. And we're going to rotate that about the y-axis. Okay, so we're going to rotate that about the y-axis. And again, we're going to get horizontal, but this time not pancakes, right? It's going to be washers. So when that hits 180 degrees, that thing's swinging around, when it hits 180 degrees, we'll get this image over here. So what will we have? Like that, and then what did I do? Did that work? We get something like that. So this would hold water, right? So this would be like some kind of very inefficient cup, okay? It would hold water, but it wouldn't hold much, right? Because it's kind of like convex. It's convex on the inside, okay? So in our solid is all this stuff in here. Okay, so we're going to use if we're sticking with what we've learned so far, it would have to be a horizontal strip, right? And then that thing will result in a horizontal washer. Okay. So we got our horizontal washer, and we know the volume of a washer. It's a little element, so it's going to be pi r outer squared h minus pi r inner squared h. And so all we need is, so what is our h, first of all? That's going to be this right here. That's going to be a little change in y, right? So that'll be a h. Okay, so our outer, so we look at our outer and we say, well, we're going to start at the y-axis is the center of rotation. So y outer is going to be from there out to the out. What is that? What is that outer radius? So it's always here, right? It's always from, no matter which washer we have, it's always out to this line, which is, so what is that radius? That radius for every single washer is the same value of 1. Do you see that? Because that outer radius isn't changing. It's always y equals 1. So this is just, oh, x, thank you. Okay, so x, but still our radius is 1, right? So if we were practicing our x coordinate, y coordinate, change in x, change in y, which one would it be? That outer radius is just an x, but we know it's the same x for every single washer. It's x equals 1. So there's our outer, that's like the whole pancake, right? The whole pancake would be pi 1 squared delta y. And then our inner radius would be, do it in red, would be from here, inner radius would be from here to here. X coordinate, Y coordinate, change in X, or change in Y? Okay, I'm hearing X, I'm hearing change in X. Now, don't get confused. It's not this distance, right? It's not like the distance of the actual part of the washer, the solid part of the washer. It's the radius of the hole, right? It's from the y-axis to the inside of our strip. So, is it X or change in X? Just X. That's just X. Yes, that blue strip has a width or a height of a change in X, but we're looking for the radius to the inside of the washer, to the hole. So that is simply X. Now, X of what? That's a changing X, right? That's the X for this curve. So what do we have to do? We have to solve that for X. So I think that's just X to the 3 X is equal to Y to the 3 halves, right? Is that right? So if Y is equal to X to the 2/3, then X is equal to Y to the 3 halves. And so that's our X value. So minus pi times radius is Y to the 3 halves squared. So there's our volume of our washer. Outside, the whole solid pancake minus the hole, right? The hole. And so then to set up the integral, we're going to have, so we got to say what are all the washers that we have. Starting at y equals 0 is that point washer right there, and then we think about all these washers up to the one that's just like a ring with all hole and no substance, right? That's at y equals, yeah, this is the point 1, 1 that we get from x equals 1 and y equals 1. So we're just going to go from 0 to 1 here. Pi. So our delta y, we can come out, so pi minus y, that ends up being y cubed. I'll just still write it as y to the 3 halves squared. Was there pi in there too? Questions? Please. Right. You could do that with geometry, right? That outside, and then you subtracted a pancake. Absolutely, yeah. So because this is x equals 1, we could actually find that what he's saying is he just found this whole cylinder using geometry. This whole cylinder, not integration. So the whole cylinder using geometry would be volume equals pi times 1 squared times 1, right? And that's just the volume of that whole thing. And then you came in here and you actually did a pancake for the hole, and you subtracted that integral. Perfectly good. Perfectly fine. Yep. It's just nice to practice setting up washers because sometimes you actually have to have washers. So it's good practice to set that up. But your approach is perfectly legit. Other questions on this one? Okay, so we're ready to. So you have a second web work on this stuff. Now that we've seen more, we've had time to think about it, see more examples. So still all washers and pancakes, and that's due Wednesday. And then we'll have a short one on the new stuff, which is we'll just start shells today. And you have 2 web works for Wednesday. The long one on this washers and pancakes, and a short one on shells. So we're going to do this example again, but instead of picking the horizontal slices, we're going to pick vertical slices. So I'll redraw this. Same example. So we got x equals 1. Okay, and so now instead of, and we're going to still rotate about the y-axis. But now instead of starting with a horizontal strip, we start with a vertical strip. And so we get a different kind of element here. We don't get a washer anymore. We start with that red thing. And so imagine that like a red pencil. Now it's gonna rotate around the y-axis. And what solid element will it form when that red pencil rotates around the? Yeah, it'll be hollow. It'll be a hollow like sleeve, right? Like a duct or a pipe or a shell. Okay, so we call these cylindrical shells. So let's draw it here. So when it hits 180 degrees, it'll be over here. And so that's what I've drawn in red. There is one of them, right? It's one shell. So I can draw it down here again. So that's something like that. So the first ones, the ones at the beginning here, will be really short and have a really small radius. And they'll get taller and taller, and each one will wrap around the one before it. Do you see that? So each one, as you move out, the next one will always wrap around the one that came before until the last one is the tallest one with the biggest radius, and it encloses all the shells. Do you see that? And that would be this one out here at x equals 1. That's the tallest shell, and it has the largest radius, and all the other shells are inside of that one. Like a telescope, right? Like a telescope. But they're not attached, right? They're all separate. Okay, so then we need how do we get the volume of one of these things? So this is called a cylindrical shell. Okay, and so what we do is to think about the volume of this thing is we come through here and get our handy dandy scissors. And we're going to cut this thing. Ow, don't cut me. Okay, we're going to cut it like that. Right parallel to the height of it, and then we're going to unfurl it. Then we're going to unroll it, okay? So then, it's okay. I'll sacrifice myself for the sake of learning. And what do we get when you unfurl it? See that? So all it is just a box, right? It's just a rectangular prism. It's easy, right? What's the volume of that? Yeah, just length times width times height. So the volume of a cylindrical shell will always used to be length times width times height. Okay, so let's start with I don't know which is which here. I guess the height. Okay, so what is the height? So let's do the height first. That's clear. The height is this one here. So what is the height of the shell? So go back and we look at our original region. Just a y coordinate, right? Remember we talked about, is it x, y, change in x, change in y? The height is just y. Okay, so we'll call the width this very small dimension here. Let's call that width. Looking back at the shell, looking back at our thing, what is the width? Well, the width is this dimension right here. What's that? Delta x. So that small dimension came originally from our slice, and that's delta x. Okay, so that's just delta x, and then finally the length is the long dimension. We'll call the length. And so what is the length? We go back to our shell. So the length, what is that distance around the shell? The distance around the shell, which is 2 pi r. Okay, all this stuff that we're doing, it will always be the same for shells. Shells will always be these circular shells that you'll imagine cutting and then splaying out, and then that will just be a rectangular shell, length times width times height. Your small dimension will either be delta x or delta y. the height, which is this dimension, will always be, either xy, change in x, or change in y. And then the length, after you've unfurled it, will be 2 pi r. So now we've got to do r. What is r? That's r right there. X, y, change in x, or change in y. She's saying x. Agree with that? The radius of the shell. It's an x coordinate, right? It's x, so also we got 2 pi x. So our volume then, so this is d delta volume of a shell. It's going to be 2 pi x, that's the length, times y is the height in this case, delta x. So which one do we need to change? Do we need to change the x in terms of y or the y in terms of x? Y in terms of x. So what is, that's that height. This y in terms of x is? That's just our function, x to the 2/3. So we got 2 pi x, x to the 2/3, delta x. Okay, so now our whole solid will be, so now x, so we're looking at what? The x coordinate, yeah, it's going to be 0 to 1. So that's going to basically be the radius. The radius starts at 0. In this case, our x coordinate is the radius of each shell. So x starts at 0, ends at 1. So we get 0 to 1. And we get 2 pi x, x to the 2/3, dx. Okay, so we want to, let's put in, so this time we didn't, remember last time in class we took the same region, we rotated it about 2 different lines, and we got different volumes, very different volumes. Remember that? The big, squatty, short kiss was a lot more volume than the real tall, skinny kiss. Okay? Now here, we're not changing the solid, we're just approaching it in a entirely different way. So the volume should be the same now. So we're finding the same solid, so we should get the same volume. So did someone write down, I know last week you wrote down that. Did someone write down when we did it by washers? Okay. So when we did it by washers, it was 0 to 1, wasn't it? Yeah. And what was it? Pi minus pi y cubed dy. Okay? So 2.356 was the volume there. And then the one we just did, 2 pi x to the, oh, you guys are simplifying things. So x times x to the 2/3. There we go. It's the same solid, we're just doing it with 2 different approaches. We ought to get the same value, and we did. And both of these are easy integrals to solve, right? Just do the math right, watch your algebra. Okay, any questions on shells? So let's have you try one more on the easy side, and then we can try maybe if we'll have time for slightly more difficult.
Although I don't know what the Y value is.
So first of all, there's the region. That's the region first of all. And then our axis of rotation is y equals -2. So what do you get when you rotate that about y equals -2? So at 180 degrees, And we want shells, right? So when we do shells, to get shells, are we going to do vertical strips or horizontal strips? Horizontal strips will create shells in this case. So we take our horizontal strip, and then that will reflect here. And we'll get the shell like this. Okay, so radius. Good question. Okay, so the radius is going to be what? From here to here. X, Y, change in X or change in Y, the radius. That's a change in Y, right? That's a change in Y. It's a upper Y, say Y2 minus Y1, where Y2 is the Y coordinate of this up here. Okay, so Y or ln X, we'll see what we need in the end. So it's going to be this Y right here. And what's Y1? So minus negative 2. So that's the radius. Y minus negative 2 is the radius. Okay, what's the height? X, Y, change in X. So the height of the shell now is on its side, like this. This is the height. X, Y, change in X or change in Y? Change in X. X2 minus X1. X2 is? The greater X is 4 minus the lesser X is? X for this, right? So X, again, for that curve. All right, so our volume, I'll just set up the volume of the shell and we can do the limits tomorrow. Delta for the shell is going to be, what did we say? 2 pi r height, in this case, delta x or delta y? Delta y, the little thickness of the shell is delta y. What did we find the radius was? Y plus 2, or y minus negative 2. The height of the shell. It's our 4 minus x, right? It's our change in x. It's that height of the shell. But we need it in terms of y. So it's going to be 4 minus x equals e to the y. It's the inverse of natural log delta y. Someone's happy. Someone got it. And then we're going to add all those up starting from, first strip is at y equals 0 is the first strip, not negative 2. The first strip that gives us the first shell is at y equals 0 up until y equals ln of 4. ln of 4. So the limits will be from 0 to ln of 4 of our dvs. The first shell is here at the bottom of the region, and that's for y equals 0. And then all the other shells, the last shell is at the y value when x is 4, which is ln of 4. Okay, so remember those 2 web work assignments due Wednesday. The longer one for washers and a short one on shells.